and it's all really confusing. So I invite you to step through it later and convince yourself that this is actually doing the right thing. But basically, you have the batch dimension, the head dimension, and the time dimension, and then you have features at them. And so this is evaluating for all the batch elements, for all the head elements, and all the time elements, the simple Python that I gave you earlier, which is query.product_t. Then here we do a masked fill, and what this is doing is it's basically clamping the attention between the nodes that are not supposed to communicate to be negative infinity. And we're doing negative infinity because we're about to softmax. And so negative infinity will make basically the attention at those elements be 0. And so here we are going to basically end up with the weights, the sort of affinities between these nodes, optional dropout, and then here attention matrix multiply V is basically the gathering of the information according to the affinities we've calculated. And this is just a weighted sum of the values at all those nodes. So this matrix multiply is doing the weighted sum. And then transpose contiguous view, because it's all complicated and bashed in 5-dimensional tensors, but it's really not doing anything. Optional dropout, and then a linear projection back to the residual pathway. So this is implementing the communication phase here. Then you can train this transformer, and then you can generate infinite Shakespeare. And you will simply do this by, because our block size is 8, we start with a sum token. Say like I used, in this case, you can use something like a new line as the start token. And then you communicate only to yourself because there's a single node. And you get the probability distribution for the first word in the sequence. And then you decode it, or the first character in the sequence. You decode the character. And then you bring back the character and you re-encode it as an integer. And now you have the second thing. And so you get, okay, we're at the first position. And this is whatever integer it is. Add the positional encodings, goes into the sequence, goes into transformer. And again, this token now communicates with the first token and its identity. And so you just keep plugging it back. And once you run out of the block size, which is 8, you start to crop, because you can never have block size more than 8 in the way you've trained this transformer. So we have more and more context until 8. And then if you want to generate beyond 8, you have to start cropping, because the transformer only works for 8 elements in time dimension. And so all of these transformers in the naive setting have a finite block size or context length. And in typical models, this will be 1024 tokens or 2048 tokens, something like that. But these tokens are usually like DPE tokens or sentence piece tokens or word piece tokens. There's many different encodings. So it's not like that long. And so that's why I think they mentioned we really want to decoder attention. Then all you have to do is this mask code, you just delete that line. So if you don't mask the attention, then all the nodes communicate to each other and everything is allowed and information flows between all the nodes. So if you want to have the encoder here, just delete all the encoder blocks will use attention where this line is deleted. That's it. So you're allowing whatever this encoder might store, say 10 tokens, 10 nodes, and they are all allowed to communicate to each other going up the transformer. And then if you want to implement cross attention, so you have a full encoder decoder transformer, not just a decoder only transformer or GPT, then we need to also add cross attention in the middle. So here there's a self-attention piece where there's a self-attention piece, a cross-attention piece, and there's MLP. And in the cross-attention, we need to take the features from the top of the encoder. We need to add one more line here. And this would be the cross-attention instead of, I should have implemented it instead of just pointing, I think. But there'll be a cross-attention line here, so we'll have 3 lines because we need to add another block. And the queries will come from X, but the keys and the values will come from the top of the encoder. And there will be basically information flowing from the encoder strictly to all the nodes inside X. And then that's it. So it's very simple sort of modifications on the decoder attention. So you'll hear people talk that you kind of have a decoder-only model like GPT. You can have an encoder-only model like BERT, or you can have an encoder-decoder model like, say, T5, doing things like machine translation. So, and in BERT, you can't train it using sort of this language modeling setup that's autoregressive, and you're just trying to predict the next element in the sequence. You're training it with slightly different objectives. You're putting in like the full sentence, and the full sentence is allowed to communicate fully. And then you're trying to classify sentiment or something like that. So you're not trying to model like the next token in the sequence. So these are trained slightly different with masked, using masking and other denoising techniques. So I think there's a bit of that, yeah. So I would say RNNs, like in principle, yes, they can implement arbitrary programs. I think it's kind of like a useless statement to some extent because they are not. They're probably. I'm not sure that they're probably expressive because in the sense of like power, in that they can implement these arbitrary functions, but they're not optimizable. and they're certainly not efficient because they are serial computing devices. So I think, so if you look at it as a compute graph, RNNs are very long, thin compute graph. Like if you stretched out the neurons and you look, like take all the individual neurons and their connectivities and stretch them out and try to visualize them, RNNs would be like a very long graph, and it's bad. And it's bad also for optimizability because I don't exactly know why, but just the rough intuition is when you're backpropagating, you don't want to make too many steps. And so transformers are a shallow wide graph. And so from supervision to inputs is a very small number of hops. And it's along residual pathways, which make gradients flow very easily. And there's all these layer norms to control the gradient, the scales of all of those activations. And so there's not too many hops, and you're going from supervision to input very quickly and just flows through the graph. So, and it can all be done in parallel. So you don't need to do this encoder, decoder, RNNs. You have to go from first word, then second word, then third word. But here in Transformer, every single word was processed completely sort of in parallel, which is kind of a. So I think all these are really important because all these are really important. And I think number 3 is less talked about, but extremely important because in deep learning, scale matters. And so the size of the network that you can train gives you is extremely important. And so if it's efficient on the current hardware, then you can make it bigger. Oh yeah, so here I'm saying I probably would have called a transformer a general purpose efficient optimizable computer instead of attention is all you need. Like that's what I would have maybe in hindsight called that paper. It's proposing a model that is very general purpose, so forward passes express it. It's very efficient in terms of GPU usage, and it's easily optimizable by gradient descent and trains very nicely. Then I have some other hype tweets here. Anyway, so you can read them later, but I think this one is maybe interesting. So if previous neural nets are special purpose computers designed for a specific task, GPT is a general purpose computer reconfigurable at runtime to run natural language programs. So the programs are given as prompts, and then GPT runs the program by completing the document. So I really like these analogies personally to computer. It's just like a powerful computer, and it's optimizable by gradient descent. I don't know. Okay, yeah, that's it. You can read the tweets later, but for now, just thank you. I'll just leave this up. Maybe. So sorry, I just found this tweet. So it turns out that if you scale up the training set and use a powerful enough neural net like a transformer, the network becomes a kind of general purpose computer over text. So I think that's kind of like a nice way to look at it. And instead of performing a single fixed sequence, you can design the sequence in the prompt. And because the transformer is both powerful but also was trained on large enough, very hard data set, it kind of becomes this general purpose text computer. And so I think that's kind of interesting way to look at it.